Good morning, gang. Welcome back. Today we're going to talk about a few things. First, it was brought to my attention that the intermediate value theorem maybe isn't something everybody saw in pre-calculus. So I want to address the intermediate value theorem in some detail for you. The other thing is the main topic for today, which is the chain rule. So today we're going to learn kind of our last big important differentiation rule. This, of course, is MAC2311. Let's do the thing. Section is OH1, that is Calc 1 Honors. And the date today is 9/22/21.
I have a questions. When is the exam?
So the exam, this is one of the things we need to talk about. Today is the day I would normally release your study guide, because today is the day we're finishing the material for exam 1, right? This section, section 3.4, is the last section that's on your exam 1. Right? After the chain rule, we're ready for exam 1. So the first exam, I would normally set for 1 week from today. That would be the normal thing. So that would be looking at the 29th for your test. That is going to be the plan. So I like after the day I give you the last bit of material, I like you to have a week to work on the study guide, think about the problems, review however you want to review. So we can set that date in stone. Exam 1, 1 week from today.
The study guide is very difficult. Will the exam the same level with the study guide?
The exam is going to be about at the level of the study guide, yes. Well, let me take a quick peek at your study guide, make sure I'm not speaking out of turn, but what we got in here? Is there anything particularly weird? Most of these are homework problems, right? These are each problems that we had in the homework set. What are we finding especially difficult?
At the beginning is homework problem, but after that, so many is not. It didn't show in the homework.
I think most of these are homework problems still. This one, 14, is straight out of the homework. This is a new one. These two are both out of the homework. I think if you spend some time going through these slowly, you'll find they're not that bad. This was a homework problem. This one is challenging. Yeah, so I would agree that number 17 here, this one's pretty hard. But I think the rest of these are not too terrible. Yeah, I would say these are about at the level of the test. The test questions, with the exception of number 17 here, the test questions will be about this hard. So if there's something in here that feels really difficult, then we should look at that. We should look and try to see why that's feeling difficult and what we can do. 13, this one is a little tricky, but I wouldn't say it's especially hard. But yeah, these are about the levels of the exam problems. This is about right. Sketching graphs, calculating limits, some definitions. I wouldn't say there's anything inappropriately hard here for test problems, with maybe the exception of 17 there. So one thing we can do, after I get through the material today, if there's a problem or two from the study guide that you guys want to talk about in a little bit more detail, we can do that. But yeah, I would say those are about the level of difficulty you can expect on the test. Today, and office hours are also a great place to talk about those problems, right? If there's one that's giving you a hard time, we can talk about those in office hours. That's a really good thing to do. Today we're going to do two things. We're going to discuss or review the intermediate value theorem. This is a theorem that is relevant to section 2.5 on continuity. And I just want to go back and have a close look at that because it was brought to my attention that not everybody solved the intermediate value theorem in their pre-calc classes. And then the other thing is we're going to cover the chain rule, which is section 3.4. The chain rule is probably the hardest of all the differentiation rules to kind of get used to. But once you're used to it, it feels very natural. So it's going to feel tricky at first, but I'll give you a mnemonic, like a way of saying it that will help you arrive at the correct answer each time. But before that, intermediate value. These things are not connected, by the way. These are pretty much totally separate things. I just wanted to talk about this because it was brought to my attention that not everybody's seen it. What the theorem says is if f is continuous on the closed interval from A to B, then for each y value between A and B, for each y value between not A and B, between f of A and f of B, there is a number C between A and B themselves, such that f of C is equal to that y value. A special case of this is something called Rolle's theorem, or not, but a special case of this is if f of A and f of B, like one is negative, one is positive, then somewhere in between you have to have been equal to 0. But this is the full general theorem. And it's easiest to understand in the case where your function is monotone increasing or monotone decreasing, something like that. So, yeah, let's look at something like this. If A is over here and B is over here, the point up here, this is B comma f of B. And the point over here, this is A comma f of A. So the y value over here, this is f of A. And the y value over here, this is f of B. And what the theorem says is that if you take any y value from in here, pick your favorite y value, whatever, as long as it's between f of A and f of B, then you can find a point on the graph between those 2 points with that y value. So for any y value satisfying f of A is less than or equal to y is less than or equal to f of B, in this case, there we can find, or there exists, a number C with A less than or equal to C less than or equal to B, such that f of C is equal to that y value. That's all. And the language of between is nicer because if your function were decreasing, these inequalities would be flipped around. One special and useful case of this is if your function is negative at one side and positive at the other side, then there has to have been an x-intercept in between.
What is this like exactly doing? Like, is it proving anything? Like, like what I get from it is like it says, okay, f is continuous. Is it just saying that like there exists a point between A and B? Or like what is it really doing?
Yeah, so that's a great question. The sort of grown-up way to think of this, think of the intermediate value theorem, IVT, as saying f of an interval is another interval. Right? In other words, the continuous image, here's the fancy way to say it, the continuous image of a connected set is connected. So what we mean by image here is the set of all outputs associated with the interval AB. So if you're starting with an interval of x values and your function is continuous, then you'll get a solid connected interval of y values associated with that, right? If this is a solid piece, then this has to be a solid piece. And one way of saying that is any y value between these two has to show up on the graph somewhere between these two. Now the language at the bottom is a little bit advanced even for this class. The word image here means you're looking at all the outputs associated with that set. So this would be like the image of the interval, right? It's f of that whole interval. I'm looking at all the outputs associated with the interval a to b. And I'm saying that that is some other interval, the interval from f of a to f of b in this case.
So is it kind of like it's showing that on like the set of y values that it's continuous in a way?
Right.
Like not like drastic changes like for like if x is going on up by like 1 and y is not going to like go up by like a billion on one of them and like come back down.
Well, so it's,
like, you know what I mean?
yes, what you're saying is what you're thinking is true. What you're saying, we need to be just a tiny bit more precise, because you could have a very fast growing continuous function. But what this is saying is what we more or less know to be true about continuous functions, that the y values can't jump, right? That I can't have like a y value. So if this is a continuous function, then every y value between these two y values, so there's the y value I get at the far left and the y value I get at the far right. And this says that every y value in between there has to get hit at some point. In other words, the y values can't be like a broken up set. Like you can't have a y value on this graph that's way up here outside of f of a to f of b. Right? Or in other words, there's nothing missing in here. That's really the way to say it, is that there isn't anything between f of a and f of b that doesn't get hit. This range, if you want to think of this as just the range of the function for this little bit of its domain. This range doesn't have any holes, right? There isn't anything missing from the range. The range is a connected set, an interval.
Can I say that if the graph at A between A and the B is a closed interval, and also their y values as f of A and f of B, they are continuous. So any y value during the f of A and the f of B, they is continuous too.
Yeah, that's an okay way to think of it. So there's a few things baked in there. The first thing you said turns out to be true, and it's not super obvious, that the image of a closed set, so if you take a closed interval here and you apply the function f to it, the image of a closed interval is going to be another closed interval. Now, this can actually get kind of weird, the way I've drawn this, the function f is monotone, right? It's increasing, it's always increasing. If that function isn't always increasing, then the range associated with that interval is not always going to be f of a to f of b. Let me show you some other examples, some other ways to think of the intermediate value theorem, and some ways to kind of not think of the intermediate value theorem. So I could say I'm going to use the intermediate value theorem to show that, what's a tough one?
I think there has the other intermediate value theorem. During the if x and the b's value y is one is in positive, the other is negative, and they will find a root.
Very good. Yeah, that's exactly what I was going to show here. Yeah. So we could try to show that this function has a root somewhere. I have to think about this a little bit. Somewhere on the interval. Let's see. Somewhere on the interval. Let's see. That would be. Ooh. Let me think about this for 1 second. I'm gonna turn off my share so I can craft this problem correctly. Because off the top of my head, I need to pick these numbers carefully. Oh no. Okay, never mind. No, that's not going to work. The one I had in mind involves the natural log function, which is no good. Yeah, here we go. Let me change this just a little bit. Let me change this to x plus e to the x. All right, here we go. Screen share back on. Share screen. Okay, so I'm going to change that minus to a plus. Say f of x is x plus e to the x, has a root somewhere on the interval from -1 to 0, right? Yeah. Let's say -2 to 0. So remember what a root is. This is a solution to f of x equals 0, right? i.e. an x-intercept. So what we're trying to do is use the intermediate value theorem to show that this function has an x-intercept somewhere on the interval -2 to infinity. So here's the deal. We know that x is continuous and that e to the x is continuous, both everywhere on all real numbers. So x plus e to the x is all real numbers. Remember, we had these theorems back in section 2.5. If you add two continuous functions, you get another continuous function. If you multiply two continuous functions, you get another continuous function, and so on. So we know that each of these is continuous. Why do we know that? Well, one, you know the graph, right? You know that both of these graphs are connected unbroken curves, pieces. Another way is using the limit definition of continuity. You can verify that for any real number, this satisfies the limit definition of continuity. This satisfies the limit definition of continuity based on the other theorems in section 2.5. So our function must be continuous on all real numbers. Specifically, f of x equals x plus e to the x is continuous on the closed interval from -2 to 0. And that's what we need to use IVT, right? IVT, if you want to apply the intermediate value theorem to this function on this interval, it says if the function is continuous on that interval, then blah, 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 blah. So this right here tells me I can use the intermediate value theorem. Hence, IVT applies to this function on this interval. Moreover, f of -2 is -2 plus e to the -2, which is like -2 plus e to the -2. That's like, you know, it's almost 3 to the -2, right? E is like 2.7. This is a rough approximation. So this is like -2 plus 1/9, which is definitely negative, right? What is this actually? 2 is 18/9. So this is -17/9, which is less than 0. F of 0 is 0 plus e to the 0, which is 0 plus 1, which is 1, which is greater than 0. So the graph of this function at -2, at -2, my function is negative. 17/9 is almost equal to -2 itself, right? 18/9 would be -2. So it's like here. This is the point. -2, comma, -2 plus e to the -2. And at 0, we have 0, 1. So what the intermediate value theorem says, or one of the things that the intermediate value theorem says, that no matter how you try to connect these points, you can't avoid crossing over the x-axis. So somewhere in here, no matter how this curve looks, I might not know, somewhere in here there has to be an x-intercept. Because the function is continuous, you can't get from this point to this point without crossing the x-axis. Specifically, by IVT, since f of -2 is less than 0 and f of 0 is greater than 0, there must be a number c between -2 and 0 such that f of c is equal to 0. And that's your root.
I think I might have missed it, but why is there a 3 where it says -2 plus 3 to the -2?
Oh, I'm just estimating E. I'm saying E is pretty close to 3.
Oh, okay.
Yeah,
Okay.
that's all. So this shaky equal sign is me doing a really rough estimate.
Oh, I didn't even notice that sign.
No worries. If you wanted to be more precise here, you could say because E is bigger than 1, E to the -2 has to be smaller than 1. So this has to be like -2 plus something smaller than 1, which still has to be negative. But the big deal here is that f of -2, when x is -2, this function is negative. And when x is equal to 0, this function is positive. And the only way to go from being negative to being positive, if you're continuous, is to cross over the x-axis somewhere.
Okay, sorry, I just missed that part where it was an estimate.
Yeah, you're good. Yeah. And this is, so like Yiping saying, this is probably the most common use of the intermediate value theorem, is to show that some function has a root. And the way you do that is by arguing first that the function is continuous, and then saying that it's negative at one side, it's positive at the other side. So since it's continuous and it goes from negative to positive or positive to negative, you have to have a root in between. Probably the most important application of IVT. So here's the whole thing. It's not too bad. The reason this is useful is because if you actually try to set this equal to 0 and solve, you won't be able to do it. This is one of those equations where no matter how good you are with your algebra, you ain't going to find that number by hand. It's just not possible. X plus e to the x equals 0 is not an equation you can solve by hand. And there are many other equations like that. So sometimes you want to know, is there a root in there? You want to say, okay, yeah, this is going to be 0 somewhere around here. It's hard to do that by hand, just jumping in and trying to solve the equation to find that root. You'll fail. Can't be done. So the intermediate value theorem allows you to approximate that. Right? I can say for sure that this number is between -2 and 0. That's a start, right? And I could refine it a little bit more. I think if I'd used -1 here, it would have worked out fine. Yeah, this would be like 1 plus 1/2 or 1/3, something like that, which is, or -1 plus 1/3, which would be negative still. So you can say it's somewhere between -1 and 0, even just by repeating this argument with a -1 here. So that's probably your most important application of the intermediate value theorem. But you should be familiar with it. Right? And before your intuition starts to run away with you, I want to show you an example. So we like to think of those endpoints as being like the smallest and the largest values of the function, but that doesn't need to be true. So maybe I'll call this like 1, 2, something like this. And actually, let me bring this all the way down to the x-axis. Why not? All right, and then I don't care what this function does outside that interval. I'm just paying attention to this. Whatever, you can do whatever the hell it is outside this interval. But the idea here the intermediate value theorem guarantees what for me here? It doesn't, right? So f of a here is 2, and f of b here is 1. So IVT promises that for any y between 2 and 1, some c gives f of c equals that y. So your function can jump outside the interval of guarantee by the intermediate value theorem. Right? It's not like the range of the function between a and b has to be the interval f of a to f of b. Right? In fact, here f of a is larger than f of b. So I want to be clear about what IVT doesn't say. IVT does not say that the range of f on a b is necessarily f of a, f of b like this. Here, here, the range or the image of the set AB would be the set 0 to 5. But f of A is 2, and f of B is 1. So IVT promises that everything in the interval 1 to 2 gets hit. Not everything in the interval 0 to 5. And when I say gets hit, right, this is an interval of y values, right? Here's the interval of y values from 1 to 2. The intermediate value theorem only promises me that everything in that little purple interval on the right is going to get smacked. So your possible locations for C's there would be like here. It doesn't guarantee any of this stuff or this stuff. That stuff can be there, but it can also not be there. It depends on how the function behaves. So I think this is kind of addressing something I think Daniel said a second ago, right? That the function won't jump way up and give you a large y value between A and B. That's not necessarily true. It can jump up and give you large y values. It's just that it has to be connected as it does so. And at some point, it's got to come back, right? So thinking about what sort of weird things continuous functions can do while staying continuous is interesting. The magical way to think of these is as they're like made of rubber, and you can stretch them and deform them, but you can't cut them or break them in any way. So intermediate value theorem for this function guarantees that for any y value between 1 and 2, there will be some C down here, some x value C, such that that y value gets hit when x is equal to C. That's what the intermediate value theorem says. It's not something that we use a whole lot in this class, if I'm honest, right? It is a cool thing. And if you were studying this material from a slightly more grown-up perspective, then we would use the intermediate value theorem often as a tool to prove things. But it's not useful for like calculation or applications or anything like that, aside from finding roots. Yeah, the word root just means intercept.
I cannot really understand, but is it my I was thinking, is it this proof? It means when the graph continues in A and B, but we cannot say the graph is continuous in f of A and the f of B, because maybe the graph when A is equal to 2, f of A is equal to 2, f of B equal to 1, but the graph maybe will equal y value maybe will equal to 5. So 5 is not in the range of 1 and 2. So we cannot say f of A and the f of the graph is continuous in the f of A and the f of B. We only can say continuous in A and B.
I would be
Is
careful
it this
about,
mean?
I would be careful about the way you're using the word continuous here. I think I understand what you're saying. So what the intermediate value theorem says here for this particular function, for this guy, is that this piece has to be connected. This piece over here, the kind of the, I'm trying to find other ways to phrase this. Intermediate value theorem guarantees that every y value between 1 and 2 will get hit, right? Guarantees that there's some point on the graph whose y value is anything in here. So you pick any number from 1 to 2. The intermediate value theorem guarantees that there will be a point on the graph between A and B with that y value. It does not guarantee the existence of things like this. And it does not guarantee the non-existence of things like this. That's where people get into trouble with that. People see the intermediate value theorem and they assume that that means from A to B, the function can only go from 1 to 2. but the function could jump way up here to 5 as long as it comes back down. Now the word continuous means something very, very particular. So what I would encourage you to do is to try to think about it in the language that I've used here. And that's that when you apply a function, a continuous function, to a closed interval, the outputs will also be a closed interval. And that closed interval has a minimum size, right? So the actual set of outputs here is everything from 0 up to 5. And the intermediate value theorem guarantees that it at least contains everything from 1 to 2. Could contain more, right? But IVT promises you that it will get at least this much. And in this case, we got more, right? We got everything from 0 up to 5, which is cool. But the IVT only guarantees this part. I can try to find some more supplemental stuff on the intermediate value theorem. I'll search around and maybe add some stuff to the module so you guys can play with this more. But we need to get to the bulk of the material for today, which is on the chain rule. The chain rule answers the question, how do we differentiate stuff like the square root of 2x plus 1 or e to the x squared? How do you differentiate composite functions, right? Oh, and I feel like I'm forgetting. Oh yeah, we need to do 3.3. We still haven't done 3.3. All right. I feel like it would be wrong for me to go over, this is 3.4. We haven't done 3.3 yet. So let me put the brakes on. I'm so sorry. Stop myself here. Before we do the chain rule, we want to talk about trig derivatives. Yeah, I'm sorry, I totally forgot. So that's section 3.3, derivatives of trig functions. Totally my fault. I forgot we haven't done this section. We need to do this section first. Yeah, so Talia's question in chat there is pretty much an accurate statement. So we're going to use the intermediate value theorem, or one would use the intermediate value theorem to guarantee the existence of solutions to equations. That's mostly the thing, right? And it's not going to tell you exactly what the solution is. It's just going to tell you approximately where the solution lives. We are going to get to the chain rule, but before we get to the chain rule, I want to talk about section 3.3 because we haven't done that yet. So we want to find in this section things like d dx of sine x, d dx of cos x, d dx of tangent x, and so on, right? The derivatives of all 6 trig functions. I hinted at the thing that we're going to need for this a while ago. Basically, what we're going to do is we're going to figure out the derivative of sine and then use our rules to get all the other guys. Sine and cosine will follow through similar processes.
Sine is the derivative. Sine is cosine. Derivative is cosine is minus sine.
That's true, but we need to prove it. So if, I'll write this in the prime notation, if f of x is equal to sine x, then f primed of x is cos x. And if, we'll call it g of x is cos x, then g primed of x is the negative of sine x. And we've seen evidence pointing this way, right? We looked at the graph of sine, we approximated the slope of the tangent line at a bunch of points, and we were able to reasonably believe that the derivative of sine is cosine from the graphs. But in order to prove this, we need a little lemma. That lemma is this. A lemma is like a little theorem, a little mini theorem. No, I won't be asking you to run through rigorous proofs on the test. I may ask you to show something or demonstrate something, but the only sort of proofs I would ask you to do on the test would be very, very simple. So the lemma is this. Lim h to 0 sine h over h is equal to 1. And lim h to 0 cos h minus 1 over h is equal to 0. So we're going to prove the lemma. And I hinted at this first weeks and weeks ago. So we're going to show that lim, I'm going to use the variable theta to 0, sine theta over theta equals 1. And we're going to do it using the squeeze theorem. Remember a few weeks back when I said I drew that circle with a sector missing and then a triangle in it, and I said you can compare the areas of those triangles and sectors to get this limit out? That's what we're doing here. So let's go through that. This is actually a pretty fun proof. So this is the unit circle. And if I draw an angle in here, theta, then there are a few different triangles I can compare. There is a little triangle in here. Then there is the area of the sector of the circle. And then there's the big triangle. Here's the area of the sector. I'll pencil shade the area of the triangle. It's a little hard to see in there. And then there's a big triangle I can draw out here that meets with this guy. So I think we would all agree that comparing the pencil to the purple to the blue because they are contained within another, the little pencil thing is the smallest. The area of that pencil shaded region must be less than or equal to the area of the sector which must itself be less than or equal to the area of the big blue triangle. Right, one is contained within the other. I'm going to find an expression for each of these in terms of the variable theta, and then I'm going to use the squeeze theorem. So what's the area of this little triangle? Well, it's 1/2 times its base times its height. The base here is 1 because this is the unit circle. And the height here, remember this point right here on the unit circle is cos theta, comma, sine theta. So the height of that little triangle is sine theta. And that has to be less than or equal to the area of the purple sector. Does anybody know the area of a sector of a circle? So if rather than the whole,
Theta multiple R.
yeah. I'm sorry, go ahead.
Theta multiple R. R is the radius, sorry.
I think it's theta times r squared over 2.
Okay.
So one way to think of it is it has to be a linear function of theta, right? Because when theta is pi, you want half the area. When theta is pi over 2, you want a quarter of the area. So it has to be a linear function of theta. And then when theta is equal to 2 pi, we want this to be equal to pi r squared, right? So we need an r squared, and we need to divide by 2. So check it out. When you plug in 2 pi, the 2's cancel, you get pi r squared. That's the area of the circle, right? Now r here is 1 because we're on the unit circle. So the area of the sector if you have a sector of radius r with angle here theta is theta over 2 times r squared. So the area of our sector, because this is the unit circle, right? This distance down here is 1, is theta times 1 squared over 2. And then what about the area of the big triangle over here? This is going to be 1/2 times his base times his height. So we got to find this height. The base is 1. How could we find the height of this blue triangle?
I think the height is the same with R.
So I don't think, not necessarily. So imagine this triangle is like way up here, right? Like this angle is way up here, then that triangle would be super tall, definitely bigger than 1. In fact, as theta approaches pi over 2, that height is approaching infinity. One way to do this is with similar triangles. So the blue triangle, I want to know what is this height. I know that this is 1. And if you look inside that blue triangle, kind of along the unit circle, there is a similar triangle hiding inside of it, whose height would be sine theta and whose width would be cos theta. So to find the area of the blue triangle, I'll draw it all out down here. I want this height. I know this base is 1. Think about the little triangle inside of it right here. I know that this point, again, is cos theta, comma, sine theta. So this is sine theta, and this is cos theta, right? Because this is on the unit circle. This point right here is this point right here on the unit circle. So by similar triangles, h over 1 is equal to sine over cosine, sine theta over cos theta. So that height is sine theta over cos theta, or tan theta. So the area of the blue triangle over here is 1/2 times the tangent of theta. We're going to hold on to this inequality.
Excuse me, I still cannot understand. Since the small triangle, I already cannot understand why you use the sine theta at there, because I think the sine theta is equal to opposite over hypotenuse.
Well, remember, we're
So-
on the unit circle. So the hypotenuse of the little black triangle down here, this is 1. But the better way to think of it, remember the unit circle is all the points of the form cos theta, comma sine theta. So the y value at this point, which is on the unit circle, is sine theta, which means that this height has to be sine theta. And the x value on the unit circle is cos theta, which means that this has to be cos theta. Is that clarifying? I can show you, let me see. There we go. This is the one we want. Of course, it's just going to take me to this right on this page. So anywhere on the unit circle, right, if you draw that little triangle, the height is sine theta and the width is cos theta. We're looking at the triangle that extends all the way up to here. So let me find that picture. Where was that? Here we go. So this works, right? So here's the little triangle inside. The black here is the unit circle. And the blue triangle, thankfully they've made ours blue also. So the height there is this height, right? This guy. And the idea is we know that this little red triangle has height sine and base cosine. We know that because this point on the unit circle is cos theta, comma sine theta. That's the definition of the trig functions. Then, by similar triangles, sine theta over cos theta is equal to this height over 1. So this height has to be sine over cosine, which is tangent. This is just one way of getting there, but I think it's the nicest way. So this is by similar triangles.
So for the small triangle, is because the triangle's area is equal to 1/2 base length multiple height. So height at here is sine theta. The base length is cosine theta. Is 1. So 1/2 multiple 1 multiple sine theta is a small triangle's area.
So there's multiple small triangles. We need to be careful here. Let me come back over here and draw one very, very big unit circle so we can actually label everything on there. So the argument here is a little bit complicated, right? I acknowledge that. This is not a super easy thing to do. There are several small triangles you can think of. Remember, because this is the unit circle, this is the point cos theta, comma, sine theta. So this height here has to be sine theta. And this base here has to be cos theta. And the triangle we're looking for is the big blue one that extends all the way out here to be tangent. This base is 1 because it's the radius of the unit circle. And if I call this height h, then by similar triangles, because they both have this internal angle theta and they are both right triangles, they must be similar. By similar triangles, h over 1, this over this, has to be equal to sine over cosine. But the little triangle that we're comparing to in our argument there is not this little triangle. It's this little triangle. So the pencil shaded triangle in our proof on the other side of the page is the pencil shaded triangle here, which is different from the little right triangle that we're using to make our similar triangle argument. But the upshot is that the height of the blue triangle has to be sine over cos. And it's true that the pencil shaded thing is smaller than the area of the sector is smaller than the area of the big blue thing. Does that feel a little better? Yeah, Talia makes the crucial observation there. The similar triangle that I'm using is not the pencil shaded triangle. The similar triangle that I'm using here is this one. The pencil shaded triangle is a little bit bigger. The pencil shaded triangle has the same height. They're both height sine theta, but the pencil shaded triangle has base 1. It's the whole radius. Similar triangles are usually learned in trigonometry. If it's not something we've seen before, then just know that two triangles are similar if they have all the same angles. And what similar means is that their ratios of side lengths are the same. All right. So this argument always takes a while to parse. That's why I tried to introduce it a few weeks ago. I'm going to take this inequality now and I'm going to work with it. First, I multiply everything by 2. And that gives me sine theta is less than or equal to theta itself is less than or equal to tan theta. Then I divide through everything by sine theta. So 1 is less than or equal to theta over sine theta is less than or equal to tan theta over sine theta. And
Will this show in the exam?
this argument, no, but the results that we're going to get out of it, yes. And I'll tell you exactly what sort of thing I'll test you on from this. So if you clean up tan theta over sine theta, you just get 1 over cos theta. So this is the same as saying 1 is less than or equal to theta over sine theta is less than or equal to 1 over cos theta. So here. And it's this inequality that's going to be super useful. Now take the limit as theta goes to 0. You get lim theta to 0 of 1 is less than or equal to lim theta to 0 theta over sine theta. It's less than or equal to lim theta to 0 1 over cos theta. The limit on the left is the limit of a constant, which is just that constant. The limit in the middle is the limit in the middle, lim theta to 0 theta over sine of theta. And the limit on the right, what is the limit as theta goes to 0 of 1 over cos theta?
1.
Good, this is also 1, right? This would be 1 over the cosine of 0. which is 1 over 1, which is 1. Therefore, by the squeeze theorem, we know that the limit as theta goes to 0 of theta over sine theta is equal to 1. Which means by your limit laws, taking reciprocals on both sides, if theta over sine theta goes to 1, you take reciprocals on both sides and you get sine theta over theta equals the reciprocal of 1, which is also 1. And this is what we wanted to show. This is what we need. So that's the proof of the lemma complete. There are problems that have you working with variations on this limit, and those sort of problems I could ask you on the test. But you don't need to go through these geometric arguments. So I'll show you how to handle those related limits as a consequence of this. But we're in the middle of something. We want to cook up the derivative of sine. Right. So this says the same thing. Is the same as saying lim h to 0 sine h over h equals 1, right? Just swapping the variable. So now that we have this, and you want to tuck this in your pocket, never forget this, right? Most people usually remember it using the variable theta. That's why I boxed this one. This is the version most people remember. But they say the exact same thing, just changing the letter. This will now allow us to prove the theorem. If f of x is the sine of x, then f prime of x is the limit as h goes to 0, f of x plus h minus f of x all over h, which is the limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. And here we're going to need a trig identity. Does anybody know how to expand the sine of x plus h? Or the sine of a plus b in general?
Sine A multiple cosine. I forget.
That's all right. I got it right here. Sine A cos b plus cos A sine b. While we're here, we're going to need the one for cosine later. Cos of a plus b is, oh shit, no, I'm worried. I forgot. I think it's cos A cos b minus sine A sine b. So I'm going to take this first guy and use him on this. I get lim h to 0 sine of x times the cosine of h plus cos of x times the sine of h, and all of that is minus sine x, and all of that is over h. Now we can rearrange, factor out some terms. I'll do it like this. You have lim h to 0. I'm going to take this first term and this last term, and I'll give them their own fraction because they both have a sine x in them. And then we'll have plus lim h to 0 cos x times sine h over h. One of these is nice. This one we know. This one, you're going to have to do a little bit more work for. So factoring out a sine here, I get sine x times cos h minus 1 over h. And then here, bringing out the cosine, I have lim h to 0 cos x times sine h over h. From the first piece, I can bring the sine x out past the limit because it doesn't have any h's in it. I get lim h to 0 cos h minus 1 over h. From the second guy, I can bring out the cos x, and I have lim h to 0 sine h. This piece, we've just shown goes to 1. This piece goes to 0. And the way you show this is by multiplying top and bottom by cos h plus 1. I'll run through it for you if you want. Normally I would leave that as an exercise, but the result here then is you get sine x times 0 plus cos x times 1, which is just cos x. So finally, yes, the derivative of sine is cosine.
How did we go from steps 3 to 4? As in step 1 being where you just wrote it out.
I took this and put them together. And I took this and put them separate, right? So I've got this minus this plus this. I take the first and last term, group them together, give them their own fraction. And I take this guy and give him his own fraction.
Oh, okay, I see. But like I know that makes sense, but what would like lead me to want to do that in the first place? Like if I were answering the problem somewhere.
Well, this is the thing about proving theorems versus like solving exercises. When you're proving theorems, sometimes there are like creative steps that aren't obvious. I'll tell you what gives me that hint. We've seen from looking at the graph, we think that the derivative of sine should be cosine. Remember when we looked at those graphs and like played the tangent line game? And I know that sine h over h goes to 1. So if I take this piece and think of it as its own thing, I know this piece is going to give me the cos x because sine h over h goes to 1. So I want this piece on its own. And that means I should put everything else together into the other piece. So it's a little bit of thinking a priori. All right, let me address the questions in chat though. So this is the one that we just worked out, right? This one was hard. This one, we worked this out using geometry. This is our geometric proof that we just did. This one, let me put a little asterisk by this one. We'll come in and take care of this guy. All right, but if you accept the asterisk, we've proved this. If you accept the asterisk, then it's true that the derivative of sine is cosine. Yeah, it is. The asterisk statement here is a consequence of the lemma. I wrote it into the lemma, but I didn't prove it explicitly. I can prove it explicitly for you. So let's just first appreciate what we have here. The derivative of sine is cosine. Remember this and never forget it, right? The derivative of sine x is cos x. Yeah, it was a part of the lemma. To see then h to 0 cos h minus 1 over h equals 0, use then h to 0 sine h over h equals 1 as follows. Then h to 0 cos h minus 1 over h can be multiplied top and bottom by cos h plus 1. And remember, everything is in parentheses. Tops and bottoms of fractions always in parentheses. So when I FOIL out that top, I'll get lim h to 0 cos squared h plus cos h minus 1 h times cos h plus 1. An identity we know. There's a lot of trig identities when you work with trig stuff. Sine squared x or h, whatever, plus cos squared h is equal to 1. So if I subtract the 1 over sine squared h plus cos squared h minus 1 is equal to 0. And then I subtract the sine squared over. So you get cos squared h minus 1 is equal to negative sine squared h. So this numerator is sine squared negative sine squared of h. And this denominator is h times cos h minus 1. Now I can split this guy up. I can treat this as negative pops out. It's a constant multiple. Then h to 0 sine h over h times sine h over cos h. Oh, this is a plus 1. I'm sorry, plus 1, plus 1, plus 1. Yeah, on the bottom here and top, we multiplied by cos h plus 1. So this is a plus 1, plus 1. All right, tops and bottom fractions, parentheses. So that's negative. This piece I know goes to 1. I'll write it out using your limit laws. Then h to 0 sine h over h times then h to 0 sine h over cos h plus 1. By the lemma, this first piece here is 0, right? By the first part of the lemma that we proved geometrically. This other piece is continuous at 0. This is sine of 0 over cos of 0 plus 1. So that's negative 0 times 0 over 2. Or sorry, 1. I'm sorry. So this piece, by the first part of our lemma, is 1. But this piece is going to 0 over 2, right? The sine of 0 is 0. The cos of 0 is 1. 1 plus 1 is 2. So you get negative 1 times 0 over 2, which is 0. This is the guy we've shown goes to 1. This guy we can evaluate just by plugging in. So it is true that cos h minus 1 over h goes to 0. So here's the full bit of work for the last part of the lemma. We use this. And the trick is to take this thing and multiply by the conjugate. cos h plus 1 over cos h plus 1. Sines, that's just from the unit circle. So remember the unit circle, every point here is of the form cos theta, comma, sine theta. And if you haven't rotated at all, you're over here at the point 1, comma 0. So the sine of 0 is 0, the cos of 0 is 1. Yeah, cos of 0 is 1. All right. So at this point, we know the following things. We have our lemma completely proved, and we know that the derivative of sine is cosine. Let's show that the derivative of cosine is nice. If f of x, or we call it g of x, right? G of x is cos x, then g prime of x. It's going to be the same sort of thing as lim h to 0, g of x plus h minus g of x over h, which is lim h to 0, cos of x plus h minus cos of x over h. Then we can expand that cos of x plus h as cos x cos h minus sine x sine h, and all of this is minus cos x over h. Now we're going to do the same sort of thing. We're going to group this first term with this last term and give that its own fraction. And then we're going to take this guy and give him his own fraction. All right. Yeah, I realize we're running out of time here. I forgot that we hadn't done 3.3 yet. So on Friday, we'll wrap up 3.3. I'll show you the derivatives of the other 4 trig functions, and then we'll talk about the chain rule. Let me finish this, though. If you can hang, please do. So I'll take that first piece, cos x, cos h, and that last piece, minus cos x, give that its own fraction. And then we'll have minus sine x sine h over h. Then splitting up the limit and factoring a cosine, pulling it out of the first piece, this is going to be cos x lim h to 0 cos h minus 1 over h minus sine x h to 0 sine h over h. And again, this piece we know is 0. This piece we know is 1. So we get cos x times 0 minus sine x times 1, which is minus sine x. So what we've gotten out of this is that the derivative of sine is cosine, and the derivative of cosine is the negative of sine. So this is the second thing you need to remember forever and ever on that. Where are we at time-wise? 12:21. Oh, we still have some time, right? No. This is 11 to 12:15, isn't it? Yeah, we're out of time. Okay, on Friday, we will cook up the derivatives of the remaining trig functions using the product and quotient rules, and then we'll talk about the chain rule. So I apologize for the disorganization today. Completely slipped my mind that we hadn't done this yet. So derivative of sine is cosine, derivative of cosine is negative sine, and these are the proofs. They are a little tricky. I invite you to look at the proof of sine theta over theta going to 1 as theta goes to 0. I think I have a thing up in your modules for this. So if that geometric proof felt really weird to you or you just didn't like it, let me see. Yeah, here it is. So here's my favorite proof why this limit is 1. And you can really take your time and digest this. They work through everything exactly as we've done. And they cook the argument up really nicely. So that's it for me for today. Again, sorry for the disorganization. Friday we'll come in, polish up 3.3 and then do 3.4. All right, it's not gonna be too bad.
I already sent the study guide draft to you. Could you help me fix it? And also, will you have office hour today?
Yes, I do have an office hour today. And if you want to send me a draft, I would be more than happy to take a look at it. When it comes to the study guide stuff, I do want you to be working mostly on your own. But if you have like a problem that you're stuck on or a problem that you're not sure about, feel free to send it to me and I'd be happy to give you a little pointer.
I already sent it to you in your emails.
Okay, then I'll get to it. I have many emails I have to answer. I think I'm not too bad, just like 20 of them today. So I will get to you, I promise, as soon as I can. But yep, I do have office hours today. Is there anything else that's burning in our brains before we close up?
No, I don't have a question. Thank you.
Alrighty then, guys. I'll see you on Friday when we finish 3.3 and then talk about the chain rule. Take care.